All right, let's get started with Lesson 1, Dynamic Equilibrium, Unit 8, Chemical Equilibrium. Now, not all reactions will go to completion, meaning that not all reactants are converted to products. In fact, sometimes products themselves will react with each other and reform reactants. In this case, the reaction is considered a reversible reaction. To indicate a reversible reaction, we use a double arrow notation as shown here in your notes. And then by tradition, we always keep the reactants on the left-hand side and the products on the right-hand side of our equation. Now, the directionality is important here. When we go from reactants to products, we refer that to as the forward reaction. But the reverse reaction, which is often called the backwards reaction, is from the products to the reactants, and we will use that traditionally throughout this course. All right, now, initially, we don't have any product. So when the reaction begins, there is no product at all, zero. And we don't get product until the reactants begin to react with each other and then begin to form product. Now, the product itself, over time, can begin to react, and then the product is going to reform our reactants. All right? Now, so therefore, if you think about it, the forward direction has an initial rate. And initially, the rate of the forward reaction is going to be quite fast, and the reverse or backwards reaction is not going to have a rate at all. It's not going to occur because there's no product. However, as the product begins to form, the rate of the reverse reaction is going to begin to pick up. And eventually, the rate of the forward reaction and the rate of the reverse reaction are going to become equal to each other. And when that occurs, we reach what is known as a state of equilibrium. An equilibrium state just means that the rate of the forward reaction is equal to the rate of the backwards or reverse reaction. All right. Throughout this unit, we are going to focus on systems that have reached equilibrium and how we can disrupt or change the equilibrium once it's been established. Now, I should make note here, and this is really important, so you might want to write this down in your notes, that equilibriums are pretty natural in nature. In other words, nature prefers to move towards an equilibrium state. Equilibrium states are very stable in nature. All right? All right, so let's look at specifics of an equilibrium system. So equilibriums are known to be more or less dynamic. Now, what does it mean for an equilibrium to be dynamic? That means the reaction does not stop, but both the forward and the backwards reaction still occur at the same rate. Now, sometimes when we look at an equilibrium state, it looks like nothing's occurring. But that's not true. The reaction is still occurring, but just at the same rate, going in the same or going in opposite directions. So the forward and the reverse reaction are still taking place when equilibrium is established. They're just occurring at the same rate. Okay? Now, equilibriums work better in closed systems, and that's because in a closed system, no exchange of matter with the surroundings occurs. So equilibrium is achieved when both reactants and products can recombine with each other. Okay? Also, number 3, this point is really super important. The concentrations of the reactants and products remain constant at equilibrium. So, what does that mean exactly? That means that both the reactants and the products are being produced and destroyed at equal rates. So remember, the equilibrium state is dynamic. The two reactions are still occurring at equilibrium. but the concentrations are fixed at that point. There's no net change in reactant product concentration since we're producing and destroying reactant and product at the same time or same rate. Okay? Very important concept to understand. All right, equilibrium can be reached from either direction. So we can actually start out with product before we start out with reactant, and it doesn't matter. Eventually, both directions, either way, we start out with a forward or reverse reaction, it will eventually lead to an equilibrium state. All right, very important to understand. Okay, let's move on to some graphing ideas. Okay, known as the equilibrium position. Now we're going to talk a lot in the next few weeks about the equilibrium position. And we need to understand what that entirely means. All right? Essentially this. The equilibrium position tells us which reaction is more favored. Is the forward reaction more favored, or is the reverse reaction more favored? If the forward reaction is more favored, then most of the reactant is going to be converted to product. But if the reverse reaction is favorable, then we're going to have a lot more reactants at equilibrium than we will have product. Now we can represent this idea of equilibrium position using some graphs. So let's make a graph here. We're going to use concentration versus time. So basically we're going to look at rate. And so if we look at the reactants of a reaction, oops, not what I want to use. A reaction here that's occurring. We know that over time, the rate of the reaction begins to decrease, as indicated by this curve, and the reactant concentration should go down over time. All right. Now let's look in terms of the product and draw it on the same graph. In terms of product, initially the concentration is really low. In fact, it's zero. We don't have any concentration. But over time, we begin to make concentration, and we'll get a curve that looks like this. All right. The rate initially is going to not be occurring, but then again, the speed up as we begin to create product. So up here, then, this represents, blue curve represents our product, and the red curve represents our reactant. All right? Now, where the two rates become equal, right about here, this is where equilibrium has been achieved. So we're going to call this the equilibrium point. Okay, this is where equilibrium becomes established, and you can see, should see, that the two rates are equal here, the reactant and product rates. All right. Now, however, at equilibrium, even though the rate of the forward and reverse reaction is occurring at the same rate, we're forming or producing product and destroying product and reactant at the same time, the concentrations are not equal. In this case, it looks like the product has a higher concentration in equilibrium than reactant. What does that mean? Well, it turns out that this is a product-favored reaction. And so the equilibrium position lies, what we call lies to the right, or product favored. Okay, so I'm actually going to write this down. This graph shows a product favored reaction or equilibrium state. Okay? Again, a product favored just means that when equilibrium has been established, there is more product, a higher concentration of product, than there is reactant. Okay? Put that in your notes. Now, what if we have an equilibrium situation where the reactant is more favorable than the product. So what that means is that the reverse reaction is more favorable than the forward reaction. So to draw this, let's do our reactant again. Our blue line, our red line is going to represent our reactant. And then we're going to use a blue line here, and that's going to represent our product. Okay, so you see the difference is once we've hit equilibrium, so we're going to say this is our equilibrium point here. So this is the point where equilibrium is reached. You can see that in this case, the reactant concentration is higher than the product concentration. This means that the reaction is reactant favored. Oops, I'll write that favored. Okay? Reactant favored reactions just mean that the reverse reaction is more common, more favorable thermodynamically than the forward reaction, so that we'll have more reactant than we have product once equilibrium has been reached. All right? So this starts getting us into equilibrium a little bit, get us introduced to it a little bit to the equilibrium position. This is it for this particular lecture video. Make sure you spend some time studying through these notes and ideas, especially these graphs on the equilibrium position. So you should be able to look at a graph or draw a graph and indicate if it's reactant favored or if it's product favored, meaning if the reverse reaction is more favorable than the forward reaction or vice versa. All right. So that's it for now. So that's it.